Hi there, my name is Ron Rogers, and this presentation is about a deadly Airbus design flaw in their flight control system. Now, one thing interesting about my channel here is I've connected with a lot of people that I've lost contact with over the years. And Tom saw my channel and he says, I got something I want to talk about, and it's very important. That's a picture of me about 47 years ago or so, something like that, out at Edwards Air Force Base. Tom actually took this picture, if I remember correctly. When you leave Edwards as a pilot, like a lot of places, you can get a book and it's full of pictures and people's signatures. I didn't obviously write anything to myself because that would have been kind of pointless, but Tom wrote one here, and of course I'm leaving and I'm going to the airline. So, of course, he didn't know about his history at the time. Now, Tom's a very interesting guy. He started out, he went through the U.S. Air Force Academy, and he started out actually as a navigator on a C-130, but then he upgraded to a pilot position, went through Williams Air Force Base, became an F-4 pilot, and was a pilot in the Night Owls out at Ubon Air Force Base in Thailand, and he has 369 combat missions. Later, he became an instructor pilot at Homestead Air Force Bases, which is where you train new F-4 pilots at the time. And he became a test pilot in 1978 at Edwards. Well, I started out there in 1977. I remember when Tom came out. Really cool guy. We had a lot of fun times. And actually, after making this presentation, we had a nice chat. And we're going to cover some extra stuff because Tom, and I haven't gotten into it yet, but Tom was also, he was a test pilot on the F-4, the T-38, and the F-15 out at Edwards, but he was also a test pilot on the SR-71 out at Palmdale. And after he got out of the Air Force and that, he became a test captain for United Airlines. I was a pilot for United Airlines. So, it's funny how small world, you're on across people. And he flew, and he's got some good stories about this. We'll cover that later. But he flew the 727, the 37, the 747, the 747-100, the 757-67, 777, DC-8, DC-10, and Airbus 319 and 320. So he's got a few stories there. But Tom and I have kind of another interesting thing in common. In 1999, I won Best Technical Paper of the Year award, published in the Cockpit magazine, which is, if you submit a paper, that's where it gets published. And I won that in 1999. In 2000, Tom won it for one of his papers on the SR-71, because he was a test pilot on the SR-71. There's a really nice picture of Tom there. He wrote a total of 4 papers, and I've read a number of them, and they're very complex, intellectual, and kind of beyond my reading ability in some instances, because that's a very interesting complex aircraft. But he's got a lot of interesting tales about it. Like I own a couple airplanes. I own a Great Lakes and a Cessna 310. Now, we all have limiting airspeeds, and I asked Tom what the limiting airspeed is on the SR-71. But anyway, my limiting airspeed, like on my Great Lakes or on my 310, it's due to, like, you could get into flutter, you could get in structural modes, things change. I don't have the problem the SR-71 has. The SR-71, like all high-speed aircraft, has a thermal problem, and the speed of these aircraft is typically limited by thermal effects. The X-15 got into some issues exploring very high speeds where it melted parts of the vehicle, and that's not good. And Tom said he could have explored the high-speed range of the SR-71, but that would have resulted in possibly melting the aircraft, and that is just not a good thing to do. So anyway, Tom, very interesting character. It was fun to reconnect with him after all these years. And we kind of share a little thing about the Airbus aircraft. I wrote a paper about 20 years ago, and I'm attaching both of these papers in the description. I wrote one about 20 years ago that talked about pilot authority and aircraft protections. Basically, how the soft protections of Boeing interacted or opposed the hard corrections of the Airbus. And I talked about them mostly in the normal configuration. But Tom's talking about an accident here where we're talking about alternate law, and it gets to be very interesting because bad things can happen, and did. Okay, so we're going to explore that, and both papers are available for download in PDF format. So I'm going to turn it over to Tom and his presentation. I hope you enjoy it because I sure did. Hi there, this is Ron Rogers, and I have Tom Tilden with us, who did a paper talking about flight protections and aircraft systems. Now, I did one, and I'm posting both these papers on the description link so you can download a PDF. Mine was about 20 years ago, and I talked about the difference between Airbus and Boeing design, but I talked about it when things are operating pretty much normally. Although I talked a little bit about some of the alternate laws. Well, there have been some issues with degraded modes in the Airbus aircraft, and Tom has put together an excellent paper, and I'll let him go ahead and explain the details of his paper. Go ahead, Tom.
Okay, so the subject is apparent speed stability, specifically as it's instituted in fly-by-wire. And the prime example of this is Air France 447. Slide. So Air France 447 was one of the most notorious accidents. It took a couple of years to get the black boxes back from the bottom of the Atlantic. So it's way back on June the 1st, 2009. The flight was going from Rio de Janeiro to Paris in an Airbus 330. It was in cruise at 35,000 feet. And then all of a sudden, the flight disappeared in the middle of the night. 228 people on board, all fatalities. Nobody knew what happened. So how does an airplane in cruise at altitude all of a sudden disappear with no warning? So it was vital they find out. It took almost 2 years to recover the black boxes, which were at the bottom of the Atlantic. Slide. That's a picture of an Airbus 330 twin engine, modern jetliner. Slide. So let's see what happened. When they finally got the black boxes back and they analyzed them, they found that was severe icing that blocked the pitot tubes, so they lost their airspeed. Now, when you lose the airspeed, a lot of the automatic systems go off. The auto throttle and the autopilot disengaged, and fly-by-wire went into alternate law. And we'll talk about what alternate law means a little bit later. Meanwhile, of course, it's the middle of the night. They're in a thunderstorm. It's dark. The first officer is presented with a whole bunch of warnings and stuff he's supposed to do. He took manual control. Now, in manual control on the Airbus has a side stick. So in manual control, the side stick is more sensitive in roll when you're in alternate law. So he over-controlled in roll. They're going back and forth a lot. And for one reason or another, he started a pull-up. Partially because of the loss of air data, he showed a little bit low. Might have just been instinctive when you're playing with a side stick to pull a little bit. But for whatever reason, he pulled up. And from that point on, his inputs were primarily pull and some push, but primarily pull. Within 1 minute, they climbed from 35,000 feet to 38,000 feet. They stalled. When the aircraft went into a deep stall, or I should say a severe stall perhaps, the right wing dropped. The first officer went full left input to try to stop it. The nose dropped. First officer went full up input. And as he held full up input, the fly-by-wire automatically trimmed full nose up in the stall. In other words, the fly-by-wire automatically made the stall a lot worse by adding full nose up trim to full elevator up command from the first officer. So in a severe stall from 38,000 feet to crash was 3.5 minutes. They were going down at 120 miles an hour. Just to give you a measure of that, if you just jumped out of the airplane, that's about how fast you'd be falling. It's about 120 miles an hour. Slide, please. Once they investigated the accident, it's a French-made airplane, and it's a French airline, so it was investigated by the BEA, which is the French authority for investigating accidents, similar to our NTSB. The causes they listed was pitot heat insufficient for severe icing. Now, the pitot heat had been certified to standards, but the icing was more than they had anticipated, so that eventually was fixed. The other causes all centered around pilot training and crew actions. If you lose air data, there's a procedure. The crew did not follow the procedure. They're saying the training could have been better, so they would follow procedure. That's as far as the BEA, the investigative authority, went in determining the cause. But an accident results from a chain of events. So were there other events that contributed to the accident? Let's look. Next slide. There's no apparent speed stability in Airbus fly-by-wire. And again, we'll get into speed stability in just a minute. In alternate law, remember they're no longer in the normal fly-by-wire law, there's no protections against stall. In normal law, there's built-in protections to make sure you can't stall the airplane. But now they're in emergency and all those protections are lost. And worst of all, automatic nose-up stabilizer trim in the stall that made the stall worse when you're in alternate law. Ultimately, to me, this is a failure of certification. The design was improper, and the certification by the Europeans and then later by the FAA did not catch this problem of nose-up stabilizer trim in stall. Next slide. The FAA and the European authorities have regulations that require certain standards for certification. The one that's applicable here is static longitudinal stability. Longitudinal is 4 aft. So what it says basically is if you have an airplane and you slow up the airplane, the elevator has to go in a direction to maintain level flight. You have to put the elevator to bring the nose up, and you have to either use the elevator or trim. But either way, as the airplane slows, you're going to have to bring the nose up, in the forces and the direction of control should be such that they has to bring the nose up with more elevator, nose up elevator, or nose up trim. The other way, if you go faster, okay, then you should have to push the nose over. Either the elevator does it or the trim does it, but something has to bring the nose over as you go faster to maintain level, and something has to bring the nose up to go slower if you're maintaining level. Next slide. That requirement is called speed stability, and you saw that in the FAA requirement. What they're really talking about, in the way I learned it, is apparent speed stability. Airplanes are not necessarily speed stable every place. For example, when you go fast, you tend to get Mach tuck, which wants to bring the nose up instead of tends to bring the nose down instead of up as you go faster. So they put in something they call Mach trim. Similarly, as you go slower, particularly with airplanes with engines under the wing, the engine's extra power may tend to bring the nose up, and you should have to bring it up. So airplanes don't necessarily have speed stability, but the requirement for apparent speed stability is that to the pilot, as you go faster, when you're level, you have to push forward and or trim forward. As you go slower, you have to pull back or trim back. And airplanes have done that for years by putting in Mach trim or speed trim. In the case of the 737 MAX that was grounded, they had such a big problem at low speed because of the bigger engines further forward that they also added the MCAS. And you'll remember that the Boeings were grounded because of deficiencies in the MCAS system. Even though the pilots messed up and the pilots should have been able to handle it, they put out guidance. But regardless of the fact that the pilots could correct it, they still grounded the airplane because of deficiencies in MCAS. So just to summarize, airplanes may not be stable, but they should feel stable to the pilot. Trim forward or push forward to go faster, trim back or pull back to go slower. And all those things that have been put in are to make it feel correct to the pilot, whether the actual airplane is correct or not. Next slide. We're in a new generation. We've gone from just manual flight controls to flight controls helped by hydraulics, and now we have fly-by-wire. Fly-by-wire puts a computer between the input from the pilot to what actually happens at the controls. So that the computer can be programmed to do whatever you want it to. So what do we want it to do? Let's look at the next slide. The simplest thing is direct law. All you would do is say, okay, if I pull half back on the stick, I want the elevator to go half in the nose up direction. If I push half forward on the stick, I want the elevator to go half forward in the nose down direction. It's simple and it's reliable. And in fact, that is the fallback mode for fly-by-wire and all the systems that I'm familiar with in Airbus and Boeing. That's the final backup. But the question is asked, couldn't we do something better to make the airplane fly better? So let's look at that. Next slide. Fly-by-wire, normal law. In other words, the way that you're flying all the time in both the Boeing and Airbus start with C star. Where did C come from? NASA did a bunch of studies when they were looking at computer control. They had A, B, C. I don't know if they had any others, but C was the determination that was used by the airline. So the current industry favorite logic is C star. They could do whatever they wanted. So let's start with C. C logic is G command. So what that means is when you pull or push on this stick, you get a consistent pitch response. It doesn't matter what your weight is, doesn't matter what your speed is, doesn't matter the center of gravity, doesn't matter if you drop the gear and the flaps. The response of the controls is going to be consistent throughout. So the airplane will always fly in the way that you want it to. G command at low speed is not as sensitive as you need. At low speed, a small change in G will cause a bigger pitch change than it will at high speed. So they modified that. And they say, okay, when we get to low speed, instead of using G, we'll use pitch rate, how fast the airplane is going, and we'll keep a consistent pitch rate. So at high speed, they use G command, and at low speed, they use pitch rate. The combination is called C star. Now, any of these, if you're going to have these parameters like G command and pitch rate, they're going to actually tell you how the airplane's going to fly, and you're going to get feedback from them. Obviously, you have to have redundant feedback from sensors for reliability. Airliners already had a lot of this. Airliners had inertial platforms, and usually 3 of them, so you had built-in redundancy. So actually, it's more an exercise in logic than adding a lot of systems when you go to fly-by-wire with redundant feedback. Next slide. Okay, so we talked about what happens when you pull or push on the stick. Generally, it's a G command. Lower speed, it's a little different, but essentially it feels the same to the pilot. What happens when you let go of the stick? And when I first checked out in the Airbus, it took me almost a week to figure this out because nobody had a good answer. It maintains 1G relative to Earth. So let's say you're flying along straight and level, and you have a decrease in power. What will the nose do? Will it drop? If you're in a regular airplane, you slow down, you don't do anything controls, the nose would drop. Will it stay at the pitch, same pitch you're at? The answer is no, neither one of them. The nose will actually come up because it's trying to maintain 1G relative to Earth. Essentially, that means flight path. You could say it maintains flight path, but if there's turbulence or something that upsets it, it doesn't actually go back to the flight path. It goes back to 1G relative to Earth. But essentially, that's flight path. Let's take an example. Let's say you're on a circling approach and you want to turn to final. You say, okay, I want to go down about a 3-degree flight path. If you have one of those flight path vectors that modern airplanes have, you can actually look at the flight path, put the flight path down 3 degrees, go into a bank, and you just let go of the controls. The controls will automatically compensate for all this, including pitch changes and including bank changes up to the limits that have been determined by the manufacturers for transport airplanes. And speed. Remember, if you're going level and you pull the power back, it will keep the nose up, and it'll keep the nose up as the airplane slows. Next slide. So that means the airplane would slow up without a pilot input. If you look at the Airbus, there's no trim switch on the controls. There's a trim wheel in the middle, like a lot of the Boeings have a large trim wheel. That's set on the ground for takeoff, but you don't touch it in flight. So on a normal Airbus flight, the pilot never trims in flight. The trim wheel does move as trim changes. Pilots don't even notice it. So trim is automatic in C star. Next slide, please. This is just reiterating what I said. Remember, with no pilot input, as the airplane slows, so I show run G relative to Earth, the airplane is going straight ahead, not necessarily level, but whatever flight path it's on. And as it slows up, it will automatically compensate for that. Notice that 1G is relative to Earth, not relative to a G meter in the airplane. Next slide. So it trims it just like an autopilot trims. What happens when you're flying? You don't make any trim input. You're not going to fly around with the airplane not trimmed. What happens is the elevator moves whatever it has to do to get the response that you've commanded. You move the stick, it says, okay, I'm going to give a certain G response, measures the G response, moves the elevator as needed to get that G response. But if you're going to stay there for a long time, it's not going to have the elevator and the stabilizer out of trim. So it will automatically trim the stabilizer to the optimum match between the elevator and the stabilizer. It's all automatic when you're in C star. Again, the pilot does not trim. It's all automatic. It works the same way as autopilot works. So there's a delay in the trim, but it will follow with an elevator that's deflected for a long time. It'll follow to get it optimum. Optimum is pretty much aligned. There are some little differences on that, but it's pretty much when they're aligned, so it acts like one airfoil efficiently. If you're in direct law, then the pilot has to trim. The pilot is now making actual inputs directly to the elevator, proportional, and has to trim. Next slide, please. Okay, so if the airplane can slow all on its own, well, wait a minute. That means it could go all the way to stall without the pilot touching it at all. That obviously cannot be done. We talked about if you're in C star, you're waiving the requirement that the pilot has to push to go faster and pull to go slower, but you're not going to let the airplane go all the way to stall, or you're not going to let the airplane go all the way to overspeed. So what Airbus does is they build in what are called protections. And basically what that means is we give up on C star and we go to another logic when we get close to a limit to make sure we don't exceed the limit. As you go to stall, all of a sudden, now, if you want to slow up anymore, you do require more force, and it's proportional to angle of attack. So essentially, they add speed stability as you get close to stall, and they stop automatic nose-up trim, so that stick gets heavier and heavier as you get slower and slower. And they add a limit for the angle of attack. So even if you pull the stick all the way back, you cannot exceed the maximum angle of attack that's been determined. Now, that's not the actual stall angle attack, that's the approach angle attack. But they determine what the limit for the angle attack is, and you cannot exceed it in normal law with protections. Next slide. Now, how about alternate law? Most crews never see alternate law. Ron, you ever see alternate law?
Yeah, well, I did a lot of flight test over in Toulouse with all of the Airbus aircraft, and when I went through training, I was an LCA on the Airbus, and when I went through training, they said, "Well, how do you get into alternate law?" And I said, "Well, I usually ask Alonso Fernando to put us into alternate law on the test aircraft, and he would do that from the flight test station." But the correct answer is multiple failures. But yeah, I did get to fly it in alternate and direct law and manual also, where we just had the trim and the rudder. Very interesting. And like you mentioned, that I found it interesting that the roll rate increases in direct law, because to get the roll rate you want, they have to have the natural roll rate much higher. So I thought it was funny that in a degraded mode, the roll rate was actually higher. But Tom, like you've said, most people never see this except possibly in initial training, if then.
Yeah, they'll see it in the simulator, but
Mm.
with a little luck, an Airbus crew will never actually see alternate law in flight. And
Mhm.
we did it in flight test also. We did it by turning off the fax. That'll put you in alternate law. So you have to have multiple failures in redundant systems. Sensors is what they say. In our case, the redundant sensors, we failed with a fax. If it's extreme failures, they'll go to direct law. Direct law is as simple as it could be, like we talked about before. but that very rarely happens. Normally, the system is going to go to alternate law if it can. So if you're in alternate law, you still are commanding G. It's the same logic that you have in normal law. The airplane flies the same. Ron mentioned the roll is different. That comes out of normal law. But the pitch law stays the same in alternate law as it was in normal law. But there's either limited protection or no protection. In the A330, there's actually two modes. Normally, what you probably saw in the A320 is in alternate law, the stick gets a little heavier, although you could actually continue to stall. In the case of the A330, without the airspeed, it went to no protection at all. So it's C star forever, right into stall. Alternate law with no apparent speed stability and no limit on automatic stabilizer trim. So the airplane, once they were slowing up, had the first officer let go, which he didn't, the airplane would be perfectly happy to keep slowing up, go into stall, bring in the automatic stabilizer trim, make the stall even worse. But he sped up the whole process. Next slide. This is just a depiction. So if you look at speed from low to high, the point is it's C star, except with protections, then C star goes away at the low speed and it goes away at the high speed. I won't go into the high speed, but it has built-in protections for high speed. Next slide. This is from the BEA final report. I'm not going to read the whole thing. Well, what it shows that they knew that in this control law, if you didn't have enough power and you were continuing to slow up, it would end up by stalling without any inputs on the side stick at all. It had they say no static stability. Again, that's really apparent speed stability rather than actual static stability. Next slide. The other thing they said, and this was really interesting to me, this behavior that we're talking about, being no speed stability, no protections, even if it may appear to contrary to some provisions of the basic regulations, was judged to be acceptable by the certification authorities. So the BEA recognized this deficiency and just said, okay, you guys say this is okay. I think that it requires more action than that. Next slide. Let's look at Boeing fly-by-wire for just a second. My experience is on the 777. Mm-hmm. Boeing has C-star, but they add apparent speed stability. You have to push forward and or trim forward to go faster. You have to pull back and or trim back to go slower. That's called C-star U. U is essentially speed along the normal axis, the x-axis, the longitudinal axis of the airplane. And this does meet traditional certification requirements. It requires trim for speed change only. All those things we talked about in the Airbus, turbulence, change in configuration, all those things, the Boeing 777 flies just the same as an Airbus. But if you change speed, you have to trim. And because of that, you have trim on the controls. The 777 has huge engines underslung. You would think that when you change power on the engines, you would get a pitch response. The answer is the airplane does get a pitch response, but you as the pilot do not get a pitch response because C-star is correcting for that. Unless your speed changes, then you have to trim. You can even have a jam stabilizer, and the 777 will fly just the same as it always did. You still have to trim for speed changes because you're still operating in normal law. Next slide. Now, what happens if normal law is lost? Why is it lost? Same reason as in the Airbus. Multiple failures of redundant sensors. There is no alternate law that maintains C-star in Boeing. If you lose normal law in Boeing, you go to direct law or secondary law. Secondary law is direct law. You're still moving the controls directly. You still have to trim on your own to trim off forces. It just has some gain changes, like whether the flaps are up or down. It takes care of some of that problem of overly sensitive roll. So there is no mode that, like the Airbus alternate law, that keeps C-star without any protection and keeps automatic trim. Again, just to reemphasize, there's no automatic trim if you go to direct, whether you're in Airbus or Boeing. You're just back to flying an airplane like you always do. Move the controls and trim off the forces. Next slide, please. Let's go back to Air France 447, take it a little bit slower. Okay, they're at 35,000 feet, and they're approaching the line of thunderstorms. It's normal there, someplace near the equator where it's called the intertropical convergence zone. And everybody that flies from north to south has to put up with this at one time or another. So the pilot flying, who's the first officer, the captain's on break, he selects heading to try to avoid a storm, and he puts in a lower speed on the auto throttle to reduce power to best turbulence airspeed. All of a sudden, wham, they lose everything. Airspeed is lost, autopilot's lost, auto throttle's lost, alternate lock. The first officer over controls. Now, what he should have done is set attitude, set power setting to a minimal power setting, and let go. And fly by wire, C-Star will take you right through, no problem. So there is a procedure for this, but he didn't do it. And he started climbing. The relief pilot in the left seat that's in the captain's seat while the captain's back said, go back down 3 times. And the first officer pushed forward 3 times. But the climb continues as the airplane slows. Why? Because there's no apparent speed stability. So when he pushes forward, he's commanding a G response to bring the pitch down a little. Now think about this. If you're in a regular airplane or an airplane C-Star U, as you slowed up, as you get slower, you'd have to pull back more and more and more and more. That's apparent speed stability. So you'd have to keep pulling back more and more and more. If at some point you did like the first officer and you push forward, you'd lose all that back pressure and be pushing forward, and the nose would come down rapidly, just aerodynamically. But with C-Star, again, it flies just like it always does, maintains flight path, makes a smooth change with a G command as required. Next slide, please. I don't want to make this overly complicated, but let's take a look at some of the data to show what I'm talking about. If you look at, I got a circled area there. The green line in the middle of that is the captain's input. So nobody's making an input on the left stick. They're not tied together. The red is the first officer line. And what I want to point out is it goes up, down, up, down, up, down. Now, a nose up command is when the red is in the down direction. That's when you're pulling up. But you can see there's short periods there where he's pushing forward, and yet the nose never comes out of a really high position. At the right side of that circle, when it goes flat in the bottom, that's when the stall, actually the wing drops off and the first officer goes full aft command. And you can see the purple line below it. That's when the elevator goes to full nose up elevator and just stays there because he holds it there. Next slide, please. This is just real quick. This is from the report. And they say at that one point there, he actually pushed 3/4 forward on the side stick to bring the nose down. Like I say, with a regular airplane, that would have brought the nose down in a hurry. Next slide, please. Okay, so let's go through the stall. In 1 minute, they climb from 350 to 380. That's higher than they should be, obviously, aerodynamically. Making large inputs. You just saw how big the inputs were in pitch and roll. They get a stall warning, which in the Airbus, it just says stall, stall. But he continues holding the nose up, making some inputs up and down, but the nose isn't coming down much. Gets into a severe enough stall. Eventually, the right wing drops. The first officer goes full left stick. Then the nose drops. The first officer goes full back stick. Then trim automatically trims full nose up, making a severe stall. How severe? It's so severe that the stall warning stops because the engineers that made the stall warning said, nah, you can't have that high an angle of attack in this airplane, but he did. Next slide, please. The line I have there, the lime green line, is the automatic trim. That's the position of the stab trim. Again, when the line goes down, that means that you're getting trim for nose up direction. And as you see, remember when that purple line went all the way down, that's when the first officer went full back on the stick. And as you can see, Around that time, the stab is starting to go there, and eventually it goes all the way full authority. Now, just a note on full authority on stab trim, with the flaps up, you hardly ever get any place close to full authority, no matter what your center of gravity or anything is. It's normally only used with flaps down when there's a moment trying to move the nose down. But this is what it did. It automatically trimmed by itself. You can see it right there in the lime green line, all the way to a full nose up. So now he's got full elevator up and full stabilizer up. Next slide, please. I don't know if you can see this. This is the popular depiction. In fact, in our airline, this is what they showed for what would happen, that the guy is in a stall coming down. That's not what happened. I mean, it shows a nice wings level, nose high stall. How could anybody not recognize that's a stall? Next slide, please. In actuality, he was in a severe stall. What happened? Again, full nose up elevator and full nose up stabilizer. He had a right bank as much as 40 degrees of bank holding full left stick. Now, it takes a while to go through the aerodynamics of this, but essentially on the back side of the lift curve, the effective aileron is reversed. The pitch varied between 15 degrees nose up, kind of like that picture, and 9 degrees nose down. There was severe buffeting, the air noise, which probably sounded the crew more like an overspeed than a stall. Again, there was no stall warning when the stick was held full back, and they were coming down at 10,000 feet per minute, 3.5 minutes from 38,000 feet to impact. The comment on the crew audio was, "We've totally lost control of the plane. We don't understand it all." Controls were working as designed. They did what they commanded them to do. Next slide. This is just a quick slide to show what I'm talking about on heading. The one that I've circled at the top, the purple line is heading, which is nice and straight. And then all of a sudden it's going almost north there. And then all of a sudden it starts changing. And if you look, they go all the way around over 180 degrees in 3.5 minutes. Meanwhile, the roll attitude, if you look at the next one down, the blue line that's circled, is left and varying tremendously. And the first officer input on the brown line below that, you can see that has gone from level initially to full up, which is full left aileron. So the first officer is putting in full left aileron, full nose up. Aileron's not moving left, rolling left. It's not coming nose up. He can't understand it. He thinks the controls aren't working. Next slide. So what should they do? Once you're in this severe stall, which was, again, brought on because of the flight control logic, they're still in C star, what should you do? Most pilots know you got to stall, push the stick forward. Next slide. Okay, he did push the stick forward at one point. And that circle there's the first officer's input. There he is. You can see it. Looks like it hits all the way full forward momentarily. And then the purple line is the elevator. And you'll notice, remember, look at the left on the purple. That's where it was before this incident. And when it goes all the way to the bottom there, that's when he's got it. The elevator is full up. And notice it goes not full up, but doesn't even go back to neutral, much less nose down. It goes about halfway. Why? It's still trying to maintain a G command. It says, okay, you had a lot and now you need a little less, but it doesn't go forward. If that was a regular airplane with direct control, whether it's fly-by-wire or not, that purple line would go all the way above neutral and would have sharp nose down input. So he should have pushed forward. And he did, but not very long. Next slide. That's not enough. Next slide. He had to hold the stick forward. If he held the stick forward, then you would eventually get more nose down elevator. G command would say, oh yeah, you really mean it. You really want to bring the nose down. So it would have eventually have given him more nose down elevator. Next slide. But that's not enough. Why? Full nose up stabilizer trim is more powerful than full nose down elevator. If you could get the elevator to go to a full nose down command, the airplane would still be stalled because The automatic trim is trimmed all the way up. The pilot didn't trim, the automatic trim trimmed all the way up. In my test, I've actually seen this in a couple of airplanes for reasons I'm not going to go into, but stabilizer trim is more powerful than the full elevator. Next slide, please. Just to emphasize, there's that stabilizer trim. And remember, it's full nose up command, and it stays there all the way to the end of the right side, which is impact. Next slide. Okay, so how do you recover once you get into this thing? Push the stick forward, hold the stick forward, and then you have to wait for automatic trim to trim the nose down on the stabilizer. You can try trimming it yourself, but it's going to fight you and it's going to have its own mind. So you have to wait for it. Next slide. So about 2 miles above the ocean. Remember, this is only 3.5 minutes from the initial incident. The captain's been called back to the cockpit. There's a discussion saying, pull the nose up. And the first officer says, quote, "But I've had the stick back the whole time." At which time the captain realizes, oh no, we're in a stall. So the captain says, no, 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 don't climb, no, no. So this is the point where the crew recognizes finally that they're in a stall, but it's too late. They're about 2 miles above the ocean, around 10, 11,000 feet above the ocean. And it doesn't matter. There's not enough time. When you're coming down that fast with the controls in that condition, it's impossible to recover. And they crash 46 seconds later. Next slide. This is to just show you, there's a family of Airbus, and Airbus went for commonality. So essentially, the fly-by-wire logic in the 330 on the bottom left is the same fly-by-wire logic that Ron and I saw in the 320. And it's also similar in other Airbus aircraft like the 340. By making it similar, then it's easier for transition. It's a big selling point for Airbus. Next slide. So could this happen again? The answer is yes, it could, and yes, it has. I have 3 examples here. One was a so-called test flight where it trimmed all the way up. I have details in my paper, or you can look it up online easy enough. But there was only 7 people on board, and they crashed in the Mediterranean, and all 7 died. Next example is AirAsia Flight 8501 from Indonesia to Singapore. Very similar, at cruise, at altitude. The way they get into it is kind of silly. There was fighting between the inputs from the captain and the first officer, but the point is that the stabilizer trim full nose up in that the timeline is similar. The airplane pitched up, stalled, crashed rapidly in a bank all the way around. And then the last one I've added is S7 Airlines, a Russian airline, on an A321, the stretch version of the A320, in December 2021. And in this case, they actually recovered the airplane. It went up and went down, but they eventually figured out how to fly the airplane using the C-Star. If you don't get into a stall, it works just lovely. And it was recovered with no casualties. Next slide, please. Okay, so this is just a summary. Remember, the causes was icing beyond capability of pitot heat and pilot error and training. I don't dispute that. Those findings are perfectly valid, and there were corrective actions taken for both of them. But I would add Airbus alternate law with no apparent speed stability into stall, automatic nose-up stabilizer trim install in Airbus alternate law. Now, there's several possible workarounds, but my final item is no aircraft should be certified that allows automatic nose-up stabilizer trim install in any fly-by-wire mode. Next slide. The last words of the first officer on 447 on the recording is, "This can't be happening." He's right. No commercial aircraft should have been certified where it was possible through pilot error to get into a condition like this that's essentially unrecoverable. It shouldn't happen. again, no aircraft should be certified that allows automatic nose-up stabilizer trim install in any fly-by-wire mode. And that's it. If we got any questions or discussion, we could, anything you got any questions on, Ron?
No, I thought it was an excellent presentation. I'm just wondering, there's a lot of geopolitics in here, and I remember when I was chairman of the AE4R Radiated Environment Design Committee, and we were putting out the certification standards for fly-by-wire. And Airbus was the one being certified at the time, and it was coming out fairly stringent requirements, and they kind of threw it back onto Boeing on the 747-400, undergoing some certification standards, electromagnetic interference, et cetera. So there's a lot of geopolitics here. And I remember when I was head of the ALPA New Aircraft Valuation Certification Committee visiting Airbus that to say anything disparage about the design or even question certain things was almost considered an insult to the French flag sort of thing. So they're very carefully politically guarding their position. So I wonder how could this be affected that the certification standards would change, especially since it looks like, well, the Boeing is fine, but the Airbus, oh, you guys got problems. I remember, as I think you probably do too, that people would be on the Airbus and say, man, this is all complicated with the facts and the sex and all these different laws. I want to go back to the 777, which is not a fly-by-wire aircraft. And then you'd go, no, it is a fly-by-wire aircraft. It's just done so well, you don't realize that it's a fly-by-wire aircraft. And I remember on my very first test flights, jockeying the throttles back and forth and the nose, just with those engines, and that amount of thrust should have been up and down all over the place, and it was just beautiful. It flew like a 767, only much, much better.
Exactly. It was actually more complicated, I think, to do that, to put in the U to require the apparent speed stability. The short-term fix on the Airbus is to say, we just won't have alternate law. You go into direct law. Now, the pilots aren't used to that at all. That means you have to pull on the stick, trim it off, and whatnot. But that would be a short-term fix. But that is no minor thing. There are some other suggestions that I have come up with. One, I think Airbus has already implemented, which is to have a backup check on angle of attack because of the XL aircraft that crashed with if you remember, the angle of attack sensors were all frozen. Well, yeah. you can derive angle of attack from inertial data, and I think they've done something like that. They've looked to make sure the angle of attack sensors are at least working. Frankly, in the case of the Air France accident, the angle of attack was still working as far as I can tell. So I don't know why they couldn't have kept the same protections. But regardless, whatever they do, the bottom line is, like I say, it should not have automatic nose-up stabilizer trim install. Now think about it. If they'd been in a stall and it hadn't trimmed full up, they would have been able to hold the wings level. It would have been like that picture in the dark. They would have been nose high, wings level, with a warning going stall, stall, stall. And as much as the crew screwed up, I have to believe that someplace between 38,000 feet and 10,000 feet, they would have been able to recover the airplane.
Mm-hmm. A nice aspect. I remember when I was doing the flight test over there, and we started out with the Airbus. I've done flight test on the 319, the 20, the 21, the 330, the 330. I think it was 500, the 340, and the various models of the 340. So I got to fly a lot of different models. But I remember when I first started flying, there was an AOA indicator down there by my left knee, and I thought that's really cool. That's nice to have. And of course, when we got ours at the airliner, that was taken off. If you could have readily looked down there and looked at the AOA indicator, if it's properly functioning, it would have told you that you were in a stall. There wouldn't have been a question about which way to pull or push.
Well, though, the other side of that is they were so overloaded that I'm not sure that they really would have recognized it. They have made some changes, and if you read the S7 report, there's a whole new system that directs them on trying to keep them in the envelope. So essentially it's another step to try to avoid getting into that situation, but it didn't work initially. And then eventually they figured it out. It's an interesting accident report if you want to read it, the S7.
Mhm.
And so it's not that Airbus hasn't been trying to do anything. They have made some changes, but the basic problem still remains that it can do this. And to me, there should be no way anytime that it can do this.
I agree. All right. Thank you very much, Tom. That's very interesting and informative and really appreciate it.
My pleasure. I've been trying to get this out for some time. And
Mhm.
you said the paper will be available for anybody who wants it. There's a little more detail in some things in the paper.
Yeah. Okay. Yeah, you just click on the description there and I'll have the links to the paper. All right. Thank you very much.
Thank you.